Okay, so the Kb value was given to us in the question. So here we have 1.7 times 10 to the negative 6. Okay, but here we would check the 1,000 rule, right? Maybe I'll do this as something separate, just to remind you. So if we take the initial and divide it by the Kb value in this case, right? This is going to be greater than 1,000. So we can then get rid of this minus x. Okay, so because of that, now we can solve for our x. So our x in this case is going to be equal to hydroxide, which is the important part here, which will then be 1.13 times 10 to the negative 3 moles per liter. So because we have that, we can now find our POH by doing the negative log of that, which will then give us 2.948. And the question originally was asking us for the pH, which means we're going to do 14 minus that value. And we need this to, how many sig figs? So we have 3, 2, so 2. So this is going to end up being 2 decimal points, so 11.05 for the pH. Okay. So our next one says calculate, basically wants us to calculate all 4 of our regular variables of a 0.6 mole per liter of this is formate. So it's like formic acid or methanoic acid. This is methanoate. So we have COO and this is HCOOH plus hydroxide. Right? So in this case, we have the initial concentration, which is 0.6000, of course, minus x, and then plus x, right? So the Kb value is going to be x squared over 0.60 minus x. So in this case, we do not have our Kb value, so we are going to have to solve for that by doing the Kw over our Ka. Now the Ka is for the conjugate acid, which is going to be formic or methanoic acid. So it's 1.0 times 10 to the negative 14, and the Ka value here is 1.8 times 10 to the negative 4. So this gives us a Kb value of 5.56 times 10 to the negative 11. So then you would do the 1,000 rule to double check, but the 1,000 rule will work. So if you do 0.6 divided by this Kb value, right? So remember when you're doing this fully on a test or a quiz or something, you should be showing this, but just to save on, we don't want this to be a 10-part video. If you do the 0.6 divided by this, you'll see that the that it is greater than 1,000. Right, so we have the Kb value here, which will then give us an x value of 5.8 times 10, or 5. Let's make this the regular number first. 5.77 times 10 to the negative 6 moles per liter. So this is equal to our hydroxide, okay? And then, of course, we can start figuring out everything else. So because we have our hydroxide, we can get the POH by doing the negative log of this value, which will end up being 5.24. Of course, to 2 significant digits for your final official answer for hydroxide would be 5.8 times 10 to the negative 6. But remember, when you are continuing on with the calculations, you want to use the extended version. pH, we know 14 minus that, which will give us 8.76, right? 2 decimal points. And then because we have that, we can get the hydronium. You could also find the hydronium by doing the Kw expression with the hydroxide. There's multiple ways. If you go back to your pH, POH lesson, right, remember there are multiple ways of determining these variables. As long as if you have one of them, really you can determine any of them. Okay, so then for our next one, we have determine the Ka and pKa values for the following. Okay, so this is an acid. Okay, so how we can tell that that's an acid, of course, is because we can see it has an additional hydrogen on it, right? It's a positive charge. So that means, let's see here. So the base originally would be this, correct? Right? So this is actually one of the Kb values that you can actually look up. So the Kb value for CH3NH2 is 4.4 times 10 to the negative 4. Now, for us to determine the Ka value, right, we're going to use this expression. And then, of course, we have this value, so we're finding the Ka. So normally, the Ka is given, but these are not really widely known weak acids. So we can still solve for it. Remember, as long as if you have one, the conjugate of it can always be determined. So the Ka is going to be Kw over the Kb. Of course, we are assuming that it is 25 degrees. We're not told otherwise. So this is going to end up being 2.27 times 10 to the negative 11. And the pKa, remember, is the negative log of Ka, right? The p of anything is the negative log of that value. So this will end up being 10.64. And actually, I believe, oh, there's no, you know what, there's no numbers to go by here. So you can leave this as is for your sig figs. Okay, so same thing here. The base version of this is N2H4, which is just neutral. The Kb for that value is 1.7 times 10 to the negative 6. So when you rearrange and solve for your Ka, you get 5.88 times 10 to the negative 9. The negative log of that is 8.23. Okay, so here we have a situation. There's a lot of practice problems for this set of questions for this section. So we have, now we're looking at very similar to what we did before, where we're trying to determine the initial weak acid concentration. You're doing the same thing, but determining the weak base concentration, right? So we have ethylamine, which is a pungent colorless gas. So we have the Kb value given. We want to know what mass of methylamine is dissolved in 250 mils to give us this pH. Okay, so the first thing to recognize is when we're dealing with weak bases, right, our Kb is always going to be hydroxide times the protonated base over the weak base, right? So we have to deal with pOH values, not pH values. So even if they give you the pH, you have to determine the pOH because we want hydroxide, we don't want hydronium. So here we get a pOH of 2.2, which would then give us, right, 10 to the negative 2.2 is going to be 6.31 times 10 to the negative 3 moles per liter. So really, I mean, the process is very similar, so I'm not going to go over this in depth, but this is essentially what our usual X is, right? So 6.31 times 10 to the negative 3 squared over X being our initial minus that, right? We want our initial concentration for our base. So our X value here ends up being 0.07741 moles per liter. Let me write this out in full. And we want to know the mass of it in 250 milliliters. So it's 0.25 liters. And to get the mass, we're going to multiply by the molar mass of our ethylamine, which is 45.08 grams per mole. Right? So going back up here, they give us the formula as well, so we can determine that. So our final answer to, let's see, our sig figs, 2 decimal points, right? So 2. So we have 0.87 grams of it. Okay, so here, very similar. So we want what concentration of this? So this is the conjugate base. So in this case, we actually are not given the Kb, so we're going to have to calculate that out. But we're told what the pH is, which we know POH is going to be 2.5, which means our hydroxide, the negative of that, to the 10 to the negative 2.5 is 3.16 times 10 to the negative 3 moles per liter. So before we can do this, right, the conjugate of this as an acid would be HCN, right? So determine the Kb, we're going to do 1.0 times 10 to the negative 14 over the Ka value of HCN, which is 4.9 times 10 to the negative 10. So it's 2.041 times 10 to the negative 5. Okay, so from here on out, it's the same as that first example. So we have our Kb is equal to x, or our original x, but it's not really an x right now, squared over x, the initial concentration, minus that. And of course, we have our Kb. So our x value here, which is our concentration of our base, and we need this to 2 sig figs, I believe. Yes, 2 decimal points. So it's going to be 0.49 moles per liter. Okay, using the Kb provided above for hydrazine, which was found in hydrazine. Hydrazine was found in one of our original questions. Given above. Okay, it must be in one of the provided oh yes, hydrazine, the Kb is in, actually if you go to page, this Kb is on page 321 at the beginning in question number 1. Hydrazine, the Kb, they give it to us as 1.7 times 10 to the negative 6. Number 1. Calculates the concentration required to give us a hydronium of this. So hydroxide would be 1.0 times 10 to the negative 14 over this. Remember, we're using this relationship. I'm going to need another part to this video. Don't kill me. So using this expression, right, we have the concentration of hydronium. So to get hydroxide, we can just rearrange that. So hydroxide concentration ends up being, let me go back to this. Oh, 1.0 times 10 to the negative 4. So we have Kb, we have the hydroxide, and then now this is going to end up being our usual suspect here over x minus that. And then our Kb value is there. So x ends up being, and we need this to 2, so this ends up being actually 6.0 times 10 to the negative 3 moles per liter. Oh boy, okay, yeah, we need another part. Whew. I was not kidding. Remember I told you if I was in class today, this would take up almost the full 2.5 hours, I bet, if I had any guess. Okay, we will continue this in the next part.